9.1 is the section on how to approximate functions with polynomials. Approximating functions with polynomials. So there is this great correspondence in mathematics with functions and polynomials in terms that you can approximate a function with the polynomial if you are carefully choosing how to work with polynomial and how many polynomials you use and so on. So we're going to discover how to represent functions like e to the x with the polynomial or sine x with the polynomial. And there will be a great benefit to that, as you will see, as you move along. And if you understand this, then you will definitely be able to work with signal processing, a lot of stuff with electrical engineering and computer science, because most of the stuff is dealt in this way. Mechanical engineers, not so much, right? You want to know your forces and integrals. So first of all, let's talk about what is a power series. So power series is going to be summation k goes from 0 to infinity, or from 1 to infinity, of ck x to the k. So observe that the k is in the exponent, right? So power, exponent, so power series. But I like to think about the word, I told you that already, I like to think about the word power as a power, because you can really do some powerful stuff with this and lessen some calculations, which we are going to see pretty soon. And I'm also going to put and immediately write the other one, ckx minus a to the k, and we will see why we would need also this, this very similar form that has minus a in it. And I'm going to box this. This is how they're defined. And we're going to write out a few terms just to get the feel that these actually are polynomials. So we start first with summation of ck x to the k from 0 to infinity. And the first term, obviously, when you k is equal to 0, you get c0. c0, right? And then it's x to the 0, which is 1. So it's just c0 times 1 is c0, plus c1 x to the 1 plus c2 x squared plus c3 x to the 3 plus dot, 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 and it's going to go forever into infinity. Now, please observe that the first term is just a number, right? c0, that 0 is just an index, that it's the first number, that it's different than c1, different than c2, possibly. And the first term is just a 0, which is actually corresponding to the linear horizontal line, right? If you have y equal 3, it's just a horizontal line going to 3. If you take a look at the first two cases, c0 plus c1, so first two terms, you are getting linear y equal mx plus b, right? And then the first three terms are the quadratic, and the first four terms would be cubic, and then you have quadric and so on, as you are going through higher and higher exponents. In general, you will never need to use more, in general, not always, but in general, you will never need to use more than 3 or 4 terms to approximate or compute anything. That's how powerful these things are. So at this point in time, even though it's a little bit early with this concept, I would like to call your attention, because all of you took some form of physics at some point, and saw pendulum. And you saw that pendulum equation, we had sine. Now, they call it simple harmonic motion, but trust me, there is nothing simple about computing that nonlinear equation. It's horrifying, actually. And it's done in a graduate course called asymptotic methods. I believe 721 or something like that at MGIT if you're taking the course. So not easy mathematics to work out. So what do we do in physics? We try to bring that concept closer to students and make it easier for undergraduate mathematics. We say for sufficiently small angles, we can replace sine x with x, and then we just compute linear one, which is nothing. Ooh, shiny. But why can we do that? Why is that possible? Well, this is the reason why it's possible. There is a way using these methods here to transform sine x, which is a wave, into the function that it's, and you will see it, it's x minus x cubed over 6, I think. And then you will, yeah. And then you'll say, wow, really, I can do that? And actually, yeah, you can add the infinitely many terms to make it more precise. But in the very rudimentary example in physics, you will just say, let's not go with 2 or 3 or 5 terms. Let's just do first term, which is just x. So technically, guys, what's happening here is you have your sine function, which does this forever. And then you have this function y equals x, which is this. Now, we all know that at this point here is pi over 2 radians. So observe that if you are to compute at pi over 2 the error between your approximation and the error between the original function is a lot, right? It's a lot. But if I zoom in and I look at this region here for sufficiently small angles, let's say less than pi over 6 or pi over 4, you see how those two lines are pretty good, pretty well aligned? Which means that the red line, computing in a red line and computing in a black line, gives us almost the same number. So that's the sense in which they say that for sufficiently small angle, you can replace sine x with x and then do calculations. But what happens if the angle is bigger? Well, remember how I told you that there is minus x cubed over 6 coming up? That is going to bend this line. And then for more than that, let's say only pi over 4, you will have better solutions and better approximations for longer than just one case. So, and we'll see how that works. I'll fire up Mathematica. We'll see some of those work very well. I hope we can get this to the normal size again. So now the question is, at this point, the question is, well, okay, we have this notion of this. What happens if I still want to use just a little bit of the equation, right? So I don't have to drag 10 terms. Can I do better? And the answer is yes. That's the second case up there. If you are to use minus a, what would minus a do in a function? Does anyone remember pre-calc 1? Yes. Left or right, right? So that a would shift everything left or right. So if you're shifting everything left or right, you can fix these things better. So now, this is extremely powerful stuff. So now, if I am to write few terms of the one that it's minus a, which is ck x minus a to the k, we're going, well, again, 0 to infinity, we're going to have, again, c0 plus c1 x minus a to the first power plus c2 x minus a squared plus minus c3 x minus a cubed. Oops. Go away. Outside. There we go. Plus dot, dot, dot. It's going to go forever. The goal is to find polynomial that will approximate the function nicely. Have you seen this before in your education? And the answer is hell yes. All of you in Calc 1, some of you I know because I had you in Calc 1, had the section on linearization. And you know the tangent line problem. Tangent line problem is the first two terms of this. Because tangent line is line, and line is y equal mx plus b, and that's exactly what you have right here. So you know how to do some of this stuff already. Now we're just going to push it past that point and add more terms. So let me first remind you that tangent line Remember that we are spelling calculus with K's because it's cool. So calc 1, there we go. Tangent line, also known as linearization. Linearization. So L of x was equal to, if anyone remembers, function computed at a plus the derivative computed at a times x minus a. And I'm just going to underline this and say it's the same thing. F prime was computed through the slope, right, through the derivative. And as you can see, there is a lot of correlation between the two. And the lines are gone. So what did we do with this? Well, if you look at this, you have the, let's say you want to compute the square root of 10, right? But which one do you know? 9, which is sufficiently close. So you're going to linearize your square root function at 9 and get the tangent line for 9. And when you have the tangent line for 9, you are going to compute your 10 in the tangent line rather than in the square root and get sufficiently correct answer. So what does it mean? Well, here it is graphically. You have a square root function which does this. And let's say that the 9 is right here, which produces 3. And 10, well, I was off by 1. Doesn't matter. And here's the 10. This is the one that you actually want to compute. So see, if you find the tangent line here, and I'm going to put that pink, you see how they match itself nicely. So this one is the tangent line, and the black one is the square root of x function. So what do we have? If you look at the linearization, you're going to have the function computed, so a is equal to 9, right, because that's the one you can compute. So L of x is going to be square root of 9 plus the derivative of the square root is 1 over 2 square root of 9 times x minus 9. As you plug in, maybe I'm just going to put f prime is equal to 1 over 2 root x, and just to remind you of that, because this tells us that the function y is equal to root x, right? Maybe I should say f of x is equal to, so it's easier. So f of x is equal to root x. So linearization function L of x is equal to 3 plus 1 over 6 x minus 9. This is your linearization function. At x equals to 9. So now you compute this at 10. Maybe I should say this way. Square root of 10 is approximately equal to the linearization computed at 10, which is 3 plus 1 over 6, 10 minus 9, because you plug in 10 for x. And what you get is 3 plus, you get 1/6. 3 plus 1/6, which is 3 and 1/6. 3 and 1/6 like this, which is 3.1666666 forever. Now take your abacus out and calculate how much is the square root of 10. Square root of 10 is approximated by, just give me the first 4 decimals, round properly on the 5th one. 3.1623. And now if you figure out how much is 1 over 6 and then add the decimals, that one will work out to be 3.1667. You see how close these are? And we didn't need a calculator anywhere to compute the linearization. It was easy because we picked a number that was sufficiently close to 10 that we can compute without a calculator, which was square root of 9. So we know that we can't find square root of 10, but we can find square root of 9, so we computed everything at 9 where we can compute, and then found the linearization, and then we plugged in the point that we want to compute actually into that linearization, and we got it. So if I change from 10 to, let's say, 28, well, then I have to change 9 into 25 because that's the closest nice number we can compute for the square root, and we go from there. So technically, a portion of this lecture today on power series, you already know a power series for the first two terms, which is the coefficient term C0 plus C1 x minus a, which is what you have in your formula right here. So now there is a proof for this, but we are going to follow the pattern, and we are going to, if you ever take my differential equations, if I ever offer it, I do this proof in differential equations class. So I'm just going to list it here. Obviously, some of this stuff is done in the book, or if you want to see me in office hours. The summation of ck of x minus a to the k from 0 to infinity is C0 plus, and now remember that what we had the, oh, sorry. Actually, no, we can use that one. Now let's use the notation of a function. So f of a plus f prime computed at a x minus a, and then the next term, I'm just going to say it's f double prime of a over 2 x minus a squared. This is quadratic approximation. And as you can see, the first two terms, f of a and f prime of a, x minus a, are identical like your linearization. That's a linearization. And we added one more term. Now, what I would like you to pay attention to is that if it's a first derivative, it's the first exponent and it's divided by 1. And if it's a second derivative, it's divided by 2 and it's a square over there. So it's going to be 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, going from term to term to term. Also, if you never realized so far, 0th derivative of a function is the function itself. You can say that the function is the 0th derivative of itself. But then dividing by 0 and other stuff doesn't work, so let's not use that. So that's the first part, little bit of this pattern. And now that you know the pattern, what's the next term? Well, it's tricky actually because this is 2 factorial, so which is 2. So the next term would be third derivative divided by 3 factorial, which is 6, x minus a to the 3, and so on. So we can do this as much as we want. So what I want to do now is to take sine function. I want to take sine function, and I want to use this method to find, let's do e to the x first, easier, cheaper. No, but that's a bad example. E to the x, whatever. So let's do e to the x. So f of x is equal to e to the x. What's the first derivative? And what's the second derivative? And what's any other derivative? So they're all e to the x, right? E to the x is not that fun. So now, what would be the a polynomial approximation for this? And let's do it at 0. So e to the x centered at 0 is approximately going to be given by function at 0, which is e to the 0, plus derivative at 0, x minus 0, plus e to the 0 divided by 2, x minus 0 squared. So we're only doing the first 3 terms, which simplifies e to the 0 is 1 plus x plus x over 2. Very good. Whoa. There's a squared. So I'm claiming right now that if we are looking around 0, in the neighborhood of 0, let's say from -1 to +1, okay? This particular polynomial function will line up nicely with the exponential function. How about we check that? Let's go Mathematica and put these graphs and see what's happening. So just give it like 10 years, it will be right up. No, I'm just kidding. It's a powerful machine.
Not iPad.
You don't. I can still draw. I know it's not iPad, but I think I did a drawing the other day. Not sure. Test page. There it is. Look at that. Yeah, it's all live. Damn it. Don't distract me. Going back to, no, calculus 3, calculus 2. So Mathematica. Here we go. I want to graph e to the x, comma, and then I want to graph all of the other ones in stages. So I want to graph the constant one, and then the linear one, and the quadratic one. So I'm just going to graph 1. I'm going to graph, oh, actually I think I have to say and 1 and 1 plus x and 1 plus x plus 1/2, which is 0.5 x squared. All right, I hope it graphs all of them on the same coordinate plane. There it is, listing all of them, so it's going to graph all of them. Perfect. Now, can we do this? So now, so the blue one is the exponential line. All right, that's the original function. The orange one, that it's a constant, that's the function 1. And then 1 plus x is the green one, which is the linear line. And then the red one is the quadratic one that we found. Observe how, as you add more terms to this polynomial approximation, the result gets better. So the only point at which they have the true answers is at 1, right? Because they all pass through 1. As soon as you move from that one, either to the left or to the right, errors start kicking in. And you obviously, the most error is present with the linear approximation as a horizontal line, which is the constant line 1. And look what happens. You see what happens if you are trying to compute the value at, let's say, half. Over here. At half. If you are looking at half, you can see that there is a lot of error, right? Almost a whole unit error if you're using the horizontal line, which is the constant approximation, just of one term, the first term. And then the linear term is already much closer to the blue line. So you are looking at the differences in y's, because if you are computing, this is the y you would get, this is the y that you get, and then these two are pretty damn close, right? So if I'm using a 3-term approximation, I'm computing in this one. Now, obviously, for number 1, you are going to have error showing up. But then, when you do the linearization, you'll have x minus 1, and that would shift everything, and it will be perfect there. That's the power of this stuff. So that's what's happening here. I hope you guys understand why these things are so. I mean, I was blown away when I saw this for the first time, because really? We can turn any function in polynomial? Wow, so how hard is the integration in the world? Because if I can write any type of function into a polynomial and integrate that, why bother with anything else? Now, please don't hang up on me now, because we already had chapter 7 and you all suffered through it, right? But the trick is that you know, these are approximations. This is not exact value. Chapter 7 is going to give you exact value when you integrate and use the trig sub and you enjoy that kind of stuff, right? It gives you the exact answer. This is going to give you the approximate answer, which Mathematica will. Yes.
That's probably like 4 or 5 following to get more precise. Or no, not 4 or 5, but like 100.
All right. I hope we understand. I hope we understand this this procedure.
How do you pick when you use 0? Or why do you pick 0?
Well, I said let's do it at 0.
Oh, okay. Well,
But I could pick any other. Well, see, you will know, because remember how we picked to do the square root at 9? Because we had to compute square root of 10, and the nice one to compute was square root of 9, right? So if I am playing with these things, right? Maybe I want to linearize around ln of 2, because e to the ln of 2 is 2, right? Or maybe ln of 3 squared or something like that, right? Yeah. So there are ways and things to do. All right, troops, let's take a look at Taylor polynomials.
Can you put the factorial problem in this, just so you remember that?
Right now, the factorial. Factorial coming in. I don't know that they're so interesting, but that's okay. I like your enthusiasm. So factorials are coming in now. So guys, the definition for Taylor polynomial would be, we'll call it Pn. The book calls Pn. It's going to be f of a plus f prime of a times x minus a to the first power plus the second derivative at a divided by 2 factorial, there you go, squared plus the third derivative at a 3 factorial x minus a cubed plus dot 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 plus whatever the nth derivative you might need divided by the n factorial x minus a to the n plus dot dot dot. It goes forever. You decide how many terms you need. 1, 2, 10, 50. And obviously you will be hopefully programming this in without, not cranking in when you need something very, very precise. So as I said before, observe the pattern. It is always the same number. Third derivative divided by 3 factorial x to the a to the 3. So 3, 3, 3, 4, 4, 4, 5, 5, 5. They always match within this one. And now, when we know this, let's take a look. What is the Taylor polynomial for f of x equals sine x? Clearly, we are going to need a whole bunch of the derivatives. So how much is f prime? Anyone? And what's the second derivative? Negative sine x. And what's the third derivative? Negative cosine x. And what's the fourth derivative? Observe that the notation changed on the fourth derivative. And let's go with one more. Fifth derivative? No, just cosine. The cool thing is that this came up now, so you don't have to anymore.
No, like I will never remember which one is negative.
You gotta stop and drop and roll. Learn it.
Well, because the derivative of sine x kind of controls you can like stay out here a couple of hours.
No, it's gonna. No. That I can. Well, I'm gonna do the same thing with Mathematica. You'll see. You see how it starts wrapping around. It looks good. Okay, guys, let's do the hard work, right? So Taylor polynomial. So this f of x equals sine x is going to be approximated by, first of all, we're going to approximate it again around 0. So at a equals 0. All right. F of a, which is sine of 0, plus first derivative is cosine, so cosine computed at 0 over 1 factorial, which is 1, x minus 0 to the first power. I have no clue why I put all these ones. It looks like they look like primes, so let's not put it there. Plus the next term is minus sine of 0 divided by 2 factorial x minus 0 squared, plus the next term is going to be negative cosine of 0 divided by 3 factorial of x minus 0 to the 3. Then the next one is the fourth derivative, so that's going to be plus sine of 0 over 4 factorial x minus 0 to the 3. And then if you have plus, that's to the fourth. Please pay attention. Thank you. And then we have cosine 0 over 5 factorial x minus 0 to the 5 plus dot, dot, dot forever. We compute what we can to simplify this. Yes, Matt?
I just want to make sure now, is this the same as the last equation that we just talked about? Because wasn't that factorial on the bottom too?
Yes.
So is there a difference?
There's no difference. I didn't write the factorials there, but it is over 1 factorial. It is 2. 2 factorial is 2. 1 factorial is 1. So
those are the same thing, the one for Calc 1 and
yes. Calc 1 is only first 2 terms of this one that has infinitely many terms, as many as you want. Yes. Kyle.
You're putting in like 0 for x, and sine x is the equation, and a equals 0. A and x are going to be the same thing.
Well, no. You get to pick a, depending on what you need to compute. Now, I said let's do it at 0 because we don't have application right now, so we're just doing whatever problem.
How did the function f in the...
Yes, The function, we are trying to expand the polynomial around 0, which means that at 0 is going to be dead on, and then around is going to be as best as possible.
Yeah, because it's f of x equals sine x, it's technically f of a equals sine a, right? You know, that's good math, that's why it's 0.
No, x is still x. The x within a sine x, that x is the x in parentheses. There are two x's at work. There is x which is x, and there is x that is a.
Yeah, that's what I'm talking about.
Okay, good.
The x that's in the function is
The x in parentheses, x minus 0, x minus 0, x minus 0, x minus 0.
yeah.
The other x is the 0, which we pick
Yeah.
regarding where we compute. All right, so we are now going to simplify this. What's sine of 0? So first term dies. If you look at the third term, you have sine 0 again, so third term dies. So any term that had sine 0 immediately dies. What are the ones that survive? Well, the first one, cosine of 0 is 1, 1 over 1, x minus 0, so the first term is just x. Do we all agree? Very good. Minus and plus gives me minus. And we have x cubed over 6, right? Are we all cool on this? And then we have plus. Cosine of 0 is 1. So 1 over 5 factorial is, very good, 120. So x to the 5 over 120. And then the pattern will continue. Because we got tired. All right? We computed. So as you can see, we computed 6 terms, but out of those 6 terms, only 3 survived because of the mathematics, right? Sine of 0. And we have those 3 terms. Guys, do you see our physics there? Sine x is approximately equal to just x for sufficiently small angles. And now when I fire up Mathematica and I put all of this in, you will see it at work. Yes?
Is that why you take 0? So you can't well a lot of them? Is that like your intention?
Yes.
Pick a number?
But as I said, if you are computing around pi over 2, you will pick pi over 2. If you are computing around pi over 3, you will pick pi over 3. You have to pick the number in the neighborhood of what you're computing. It's not just what's convenient.
Yeah.
It should be convenient as much as possible close to the place where you must be to do the computation.
So how do you know what's 10?
You look at it with your eyes.
What, just that's a problem?
Yeah, because remember how when I took square root of 10, square root of 9 is 3. So I can do square root of 9. I also know that the square root of 121 is 11, but 11 is way, 121 is far away from 10, which I needed to compute. So I used 9.
What is that answer for? Like, we got that answer, but what is that answer?
That's my next story. It's coming up in 17 seconds. Mary, you have 17 seconds.
Okay, this might be a stupid question to waste 17 seconds on, but can you just run through how you got number 20 out of 5?
It is 5 factorial, so it's 1 times 2 times 3 times 4 times 5. So 1 times 2 is 2 times 3 is 6 times 4 is 24 times 5, 120. It's a 5 factorial. You multiply all the integers up to that value. And remember that 0 factorial is 1.
Can you have 3x as factorial? Or you can't have variables as factorial?
No variables. Plus, this is defined this way, so don't mix x's there. Please don't invent new mathematics. We're good. This works. Just learn what is there. It's easier. Now we get to the extremely important question. This is, guys, the most important thing for this section, for this concept. What is this good for? Why are we wasting our time with this, if we are wasting time with this? So we have that sine x is approximately equal to x minus x cubed over 6 plus x to the 5 over 120 minus, it will go like this forever. Well, how many of you know the proof of why the derivative of sine is cosine?
Isn't it when the letter I
Yeah, no, with limits. Yeah, and then we had to use the sign of sum of two angles, and then we had to memorize the two limits and so on. So what did you say? I'll just memorize the derivative sine and cosine. Maybe. Right? You took the easy way out. Instead of proving it every time you need it, using the limit definition of the derivative, with all bunch of trig functions in identities following along, you took the cheap way out, and you said, I'm going to memorize the derivative of sine is cosine. But guys, what happened here is your sine is now polynomial. What's the derivative of this? It's 1 over x squared over 2 over x to the 4th over 24, right? You take derivative like this because it's polynomial. The purpose of this section is to take whatever function, whether it's nice and friendly, whether it's nasty, and turn it into the polynomial. And polynomials, you can integrate and differentiate like this. You have to think about it twice. That is the power of this section. Turn any function, whether it's transcendental, whether it's whatever, into a polynomial. Obviously, if the function is already polynomial, you would not gonna, right? You're just gonna get it back, the same polynomial, because this is polynomial approximation. Yes?
So what is this useful rule?
I just said that. You take whatever function and you turn it into a polynomial, and this thing easy to differentiate, easy to integrate, easy to, so no partial fraction, no trig sum, no u sum, nothing. Because you have polynomial, and polynomials go like this in integration and differentiation. Easy to compute, some exponents, you multiply, you stick, sand, you're good to go. Yes?
On the lab, there was like an integral of ln of x. So you can just use the
Perfect. Yeah. You can
This is the boss.
that is your section 9.4, guys. Do you honestly think that the engineer will sit there and crank integration by parts or anything?
Of course not.
Oh. Yes. Well, now in Mathematica, but let's go back to engineer 20 years ago. The extent of mathematics they need for their field across all fields is just this. Don't need anything else. First 3, or if you need bigger precision, 4 terms of that. And that's it. And the next term over here would be minus x to the 7 over 720. That's it.
Yeah.
So let's fire up Mathematica again and see how well this works. Because maybe it's lousy and we can just all go home. Because all right.
Oh, wait, really?
I know.
I'll let them two go first. They all have like drinking water, yeah. Time.
Yeah, for those of you who joined in live, apparently what happened is 6 students decided to leave. As I said, we're going to take a look at Mathematica.
Well, since you already acknowledged it.
So we're going to graph sine x and x plus x cubed, no, x minus x cubed over 3 divided by 3. Oh no, I have to do this. Give me an hour, I'll be right with you. Just need to type this in. And plus x to the 5 divided by 120. Boom. Yes?
Like you're not, if you're trying to find like, I was gonna say like when you're not really like, if you're in like a field or you're not given a function ever.
That is your job to find it. And they're never pleasant. And that's why you want to use this.
And you can use that to find.
So guys, here is the purpose of this lecture. And we have to do this quickly before the other student that left to come back. Okay. It doesn't color code here, so I'm not sure which function is which. We all know that's x. We all know. I think sine is the blue one. Yeah, blue is the sine. So you see, blue is the sine is the blue line, and you can see all of these. Maybe if I let me try to actually get better result over here. On negative pi to pi. I hope this is going to give us much better result. All right, so here we go. There we go. So you see that they start curving, right? So the more terms you put, the better approximation you get. And, oh, there's the legend right here. So blue one is the sine x is the original one, and then x and x minus 7 plus x. Good, so they're all good. All right. So you see that that's the pi, 314, right? That's the pi where the sine hits. And you see that at pi, it's horrible at pi to use any of these to compute. And that is the purpose of that A. As you can see, blue line and all other lines are very well approximated right here in the middle at 0 because we did this expansion at 0. And these formulas that we got, because we computed at A equals 0, are guaranteed to work well around 0. And lousy everywhere else far from 0. So if you, as you can see, already at 1, we have discrepancies that are big enough to be useless. And then as you are moving away from it, it gets rapidly worse and worse and worse. So what we are doing over here is we get these pieces. Now, if I am to redo this problem and center all of this at a equals to pi, you would get this kind of behavior, this kind of a perfect fit here. And it would be this lousy right there. Because it is good, it's perfect, and it's very close, only at the places where you compute where your A is. So A is equal to 0, A is equal to pi over 2, A is equal to pi, or pi over 6, whatever you have to use for your application. Now, I had a question as the, I'm just waiting for the cruise ship to pass. By the way, we are, for those of you watching live, we are based of the Ocean County, and this is the... And this is the Ocean Trip 101. So the big question and a good question is application of this, and 9.4 is the one to give us the application in terms of let's integrate, let's differentiate, let's do all that stuff. You as engineer have to be able to come up with a function to integrate. You remember how I bothered you much? In the very first chapter we covered, we had those rotations, right? And what did we rotate? We rotate silly stuff that you can compute easy because, you know, we want to have easy integrals to compute as exercise. Now, does this function over here look to you as x or sine x or e to the x? No. This is going to be some horrific function that might have e to the x embedded into hyperbolic sine that all together is multiplied into tangent. Doesn't matter. It's going to be something insane. Those are the functions that you deal with as engineers. And that is the part of modeling, the thinking that you guys have to figure out. That you guys have to know how to get it. So now, looking at these numbers here, well, sorry, at the function here, it might be very nasty to put that in a rotation integral, square it for your disk method, right? Square it and then compute. But if you are able to take that function and turn it into a polynomial like this and integrate, we're done. And you need a little bit more precision, you add one more term. We'll see how that works. Then, that is something that, now obviously, right now you have Mathematica, you put whatever integral there and just grind through it. Only if you have improper integral, you have to worry about where the discontinuity is and so on. Yes?
So to compute that one, we need to set a limit then. Otherwise, it won't end. The polynomial.
Well, you pick how many terms you want. Generally, you want 3 or 4.
Okay.
Generally, you want 3 or 4.
So,
So in order for the sine function, the one that we just did, in order for me to get 3 terms, I had to compute 1, 2, 3, 4, 5, 6 terms. I had to compute 6 terms.
to get 3 terms.
Yeah, because sine of 0 is 0, 3 terms died, and I have 3 terms that are there.
Okay, so basically,
You first. Yes.
Yeah, so basically, we just need to compute until like 6 terms.
Well, in some cases, it's not going to cancel at all. For ln or for e to the x, you just compute first 3 or first 4. It is, you know, when you start doing and you say, you know, you plug in 0 and you go, that one dies, so I can't count. That one I keep. That one dies, right? You will know immediately how far you have to go. Yes?
Are Taylor polynomials only used for functions that have infinite sets of derivatives, or is it for functions that you derive 5 times and you get to a constant?
Well, the only function that you can derive 5 times and get to a constant would be a polynomial, and why would you turn a polynomial into a polynomial? So technically, you will not be using this on polynomials, because polynomials are already easy, right? You will use this on e to the x squared, e to the sine x. You would use this for ln x. You would use this for any of those crazy things.
Wouldn't you still take the derivative of it?
Yeah. But you will see that there is a table of all of these expansions that you can memorize, and I don't think it's useless. There is Mathematica now for your field. We just practice Mathematica now. So that's it. You know, look fun, but it's a very good exercise. Yes.
So this is our final answer. Do you want us to write it in higher exponential?
Oh no, that's fine.
Do you plug anything in for x?
If you need to compute, yes. If you just need it, if you need to integrate, and then later you will use the limit of integration. There you go. Yes. Yeah.
So like the more terms you add to it, you know how it seemed like the 3 or 4 versions of sine x you had of like different amounts of Taylor series?
Yeah.
So the more terms you have, the more it looks like it's linearized with the original function.
Yes. The more terms you put in, I believe the next term is 100. It's x to the 7 over 720. Let me re.
We didn't tell us from the beginning.
7 factorial is like 5,044.
Oh yes, because 6 is it's 120 times 6 is 720, and then 5,000. So what's the seventh term? Let me just write it.
1/540.
X to the 7 divided by 5,000. 040, right? Very good. Okay, so I'm going to go back into Mathematica now, and I'm just going to add that, which will produce another line on our graph, and we'll see that it is going to be even better. So over here, I'm just going to copy this one. And Control V minus x to the 7 divided by 5040. 5040, right? All right, it's thinking. It didn't come up. It's not that funny.
So the graphs that last like the longest, so close to the original, have the most terms in it.
Yes. In this case is one of these colors that I would not know name for. I technically know.
It says right down to the right.
Yeah, it does, but I don't know what the name for it would be. So. It's the private cruise ship. So it's
Teal color?
the teal color. I thought that was a name. All right, it's a name for a color, right? So there, yeah, the one in the middle over here, but it should peak higher, closer to the blue, over there, because that's where it should work better. So the more terms you put, the better it curves, the closer it gets, and that's how this stuff works. It's awesome. All right, so now we know how to find these things. And finally, guys, we can take a look at something really, 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 really cool. And that thing is the derivative of sine is cosine. Because the derivative of sine is cosine x, which means that this thing is 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 720 plus dot 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 forever. Now 720, yes. Oh, I didn't catch 0. Okay. So looking at this, you would say, well, yeah, you took the derivative. Yeah, I did take the derivative, but you know what? You can do this procedure for cosine. And if you do this procedure for cosine, completely independently of what we did for sine, you're going to get this. And you would realize that they actually match. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Now, why is that so? Well, take the derivative of cosine here. What do you get? What's the derivative of x squared over 2? It's negative x, right? And the derivative of this is plus x cubed over 6. And the derivative of this is minus x to the 5 over 120. Plus dot dot dot. Do you see how the red one on top and this one are exactly the same? They're all opposite signs. Factor out minus, and there you go. How cool is this? It's extremely cool. And also, it's about 250 years old. Mm-hmm. I know.
It's a failure.
Yeah. Yeah. He was working on this for his PhD. Now you do it for homework. Like nothing.
We should get better grades.
It's called academic inflation. So. You know more mathematics than you can ever do. No. And yet you're still 250 years behind of where stuff is now. Exactly. To study. You want to be in the current field, you have another 250 years of math to catch up. That concept is 250 years old. I remember my first lesson in linear algebra. Sorry, no, differential equations. No, linear.
Is
No.
new math discovered every year? What's being discovered right now?
Hyperdimensional numbers, algebraic topology, they're just forms that you can't. The hierarchical there is stuff that is coming up every day. And it's awesome.
That we don't know.
Yeah, that we don't even know.
Why do you
Yeah.
know this exist?
Why we're not learning. They don't even know themselves.
I was thinking that now.
Yeah, well, at least Dick's lecture is done, so let's stop.
Over a hyperdimensional number.